Okay, then yeah. Welcome everyone to the weekly colloquium of the Physics Institute of the UNAM in Cuernavaca, Mexico. Our guest today is Massimiliano Di Ventra of the University of California in San Diego. Let me say some very few words on the vita of Massimiliano. So he did his PhD at the EPFL in the Swiss, and he has been a visiting scientist at the IBM Watson Research Center and a research assistant professor at the Vanderbilt University before joining the physics department of the Virginia Tech in 2000 as a professor. And since 2004, he's a professor at the University of California in San Diego. Yeah, his research interests are in the theory of quantum transport in nanoscale and atomic systems, non-equilibrium statistical mechanics, DNA sequencing, and polymer dynamics in nanopores, and recently memory effects in nanostructures for applications in unconventional computing and biophysics. Yeah, he has published more than 200 papers in scientific referee journals, which accumulate in total more than 25,000 citations. He has 4 patents, is author of various books, for example, the textbook on electrical transport in nanoscale systems. He has been visiting professor at various universities in the world, at the Technion, the Technical University in Dresden, the University of Paris-Sud, the Technical University of Denmark, just to mention a few of them. And he is co-founder of the company MemComputing. So Max, thank you very much for accepting our invitation to give this colloquium today, and we are looking forward to your talk.
Okay, well, thank you very much, Thomas, for this nice introduction. Thank you all for coming. Let me just take this off so I don't have issues with this. Thank you again for this invitation. And I've been working a lot on transport in the past, but I switched to recently, although I do a little bit of work on transport still, but I've been mostly working on a new computing paradigm I call MemComputing. And as Thomas was saying, we actually founded a company with the same name, so not much imagination there. If you're interested, you can go on the website of the company, and the company just released the software as a service so that you can actually test, or reproduce some of the things I will show you today. And there is also, I'm actually under contract with Oxford University Press for a book on this. Hopefully will come out this year. But if you're eager to understand a little bit better what this computing paradigm is all about, I would suggest you go into this perspective, which is a much simpler introduction to the subject. And of course, I have funding from several agencies. So let me start by discussing what type of problems we want to solve. Okay, so why we want to come up with a different computing paradigm. And by the way, you can stop me anytime. I believe you can unmute yourself and just stop me. So we want to solve combinatorial optimization problems that are really tough. And you find them all everywhere, including in physics, when you try to find the ground state in a non-convex energy landscape. That's a very tough optimization problem, right? But you find it also in, flight scheduling and routing, chip design. For example, if you want to test the chip that it comes out of a fabrication facility, you have to, solve a very complex optimization problem, electric power distribution, how the electricity distributed and so forth, right? So autonomous vehicles, responding to environments and many more. So this is a class of problems that is particularly difficult to solve. In fact, mathematicians, computer scientists call them NP complete, NP hard, in the sense that it becomes exponentially difficult to solve them with increasing size of the problem. So this is the type of problems we want to tackle. And how do we do it nowadays? Well, we use a paradigm that was introduced by Turing more than 80 years ago. It's called the Turing paradigm, in fact. And without going into the details, it's essentially a mapping between a finite string of symbols to a finest string of symbols. Typically, these are zeros and ones, but you could have any type of finite strings. And in between, what we call transition function is an algorithm, right? So that's how we solve these problems. We, let's say factorization or some other problem, you literally come up with some algorithm that tries to, find whatever is the solution of the problem. Now, is there an alternative? In particular, can we use physics? Since we're physicists, so is there an alternative that allows us to, instead of using algorithms, can we use physical systems to compute? And you have heard, I'm sure, about quantum computing, which is a big deal. There is a lot of research, which uses, in fact, the physics of entanglement to solve some problems efficiently. For example, factorization. There is an algorithm that allows you to solve factorization polynomial time if you use, entanglement between qubits. There is, however, a problem with quantum computing because you cannot simulate a quantum computer in software efficiently. So you cannot just take a quantum computer and you, write down the equation of motions of that computer and try to simulate this computer in software. So you need literally hardware to do that. So there is no alternative in quantum computing. You need to have hardware. And if you want to take advantage of quantum features like entanglement, then the hardware has to operate at extremely low temperatures, typically cryogenic temperatures, right? So this makes this computing paradigm not easily scalable. It's very tough. And there has been a lot of progress. Several suggestions using all sorts of devices, but it is tough. It is difficult to scale up. And again, it cannot be simulated in software because you're handling a system whose Hilbert space explodes exponentially. So you have to do it in hardware. But it is a sort of a misconception to think that quantum phenomena are the only ones you can use to do computation. In fact, you can do computation with any physical system. For example, here I show you a pinball machine where I let a ball, right, go down. And if there are no other, there are no local minima where the ball can get stuck, it will bounce off the pop bumpers until it goes down thanks to gravity, right? So if you think about it, the ball actually, when it goes down, calculates its own trajectory, right? As we interpret it as a trajectory, the ball doesn't know it's doing anything. It has to do whatever it has to do, right? Once you set it up, that thing will go down. In fact, you can shake also this machine, right, the pinball machine, and it will still, unless you shake it so much that you destroy it, the ball will go down and get out. So I can actually even put a photo detector here and ask the question: is the ball exiting or not, right? So physical systems are incredibly powerful because they have no choice. If you design a physical system to do something, right, it has to render an action stationary, and so it has to, find the trajectory that renders that action stationary. Not only that, if you design them to solve any problem, they actually have no knowledge about the difficulty of a problem. They don't know whether mathematicians say that this problem is easy, tough, or whatever, according to some mathematical definition. They have to do it. So the goal, my goal is precisely to use physical systems, of course, designed in an appropriate way, so that when they're designed to solve the problems I told you at the beginning, combinatorial optimization problem, they will do it because they have no other choice. So the important thing that I want to make here is that we need to maintain, however, the input and the output digital, in the sense that we want the input and the output we want to be able to read and write the input output with a finite precision, right? So independent of the size of the problem. That's critical. That's very important. Otherwise, you wouldn't have a scalable machine, right? Because if the input or the output or both are real numbers require, in principle, an infinite amount of bits to be represented. So you would have an analog machine, and an analog machine is susceptible to noise. So it's very difficult to scale. So we want to have input and output digital, so we have no issue with the precision and scalability of the machine. So that's a very important point that we need to make. And the other thing is that we want it to be easy to fabricate. So we don't want to go the route of quantum computing. We want to actually use, if possible, even present technology, or at least something that allows us to build these machines in hardware now with present technology. So what I will show you in this talk is that if you have a physical system with memory, a time no locality, memory is for us physicists a time no local property of a physical system that maps integers into integers, let's say 0 and 1s, then I will show you that these are actually very efficient in solving very complex problems, like the pinball machine will go down, the pinball will go down the pinball machine without knowing that it's solving anything. So we introduced a concept that we call universal MemComputing machine, and the idea is that instead of having a separation of tasks between a CPU and the memory, like we have in our computers, like our laptops, we imagine that everything is done by a unit we call computational memory or mem processors, that does both the storage and the computation. And the computation is done using time no locality. And then apart from a control unit that tells the machine what type of program to execute and an input and output, there is no flow of information outside the machine. That's important. In our von Neumann type of architectures, right, the CPU has to exchange or take information from the memory bank, and this flow of information back and forth between the CPU and the memory is really the bottleneck, both in latency time and energy that our computers expand when they do computation. We don't want that. We want that the whole computation is done on the same physical location without moving out of the machine. Like you would have here in the picture, you have a collection of these MEM processors, like a neural network, but I will tell you in a second that to solve the problems I showed at the beginning, these neural networks have to have a very well-defined topology. And then the state of the machine starts in the machine, and then you let it evolve. The state changes, but it never leaves the machine. So it's always inside the machine. And so these are objects computed with and in memory, and I will discuss only digital. You can always define them also as analog, but as I told you, the digital ones are the scalable, and that's the only ones I will discuss in this talk. Of course, you can formally define them like Turing did with his machine. I write here the definition, but I won't go into the details. If you're interested, you can take a look at the paper. But you can define this so you actually know what type of problems they can solve. In fact, they are universal in the sense that they are Turing complete. They can simulate any Turing machine, but they're not necessarily equivalent to Turing machines. At least we haven't been able to prove that mathematically. So is this only math, or can we build them in hardware? So that's the question that we physicists have to ask, right? So in order to answer this question, let me give you an example. Suppose you want to solve a Boolean problem, one of those problems I mentioned at the beginning, like factorization or finding the ground state in a non-convex landscape. Now, for those of you who are not familiar with this, any of those problems, which are called combinatorial optimization, can be written in this form that I just wrote here, where you have variables, x1, y1 can be true or false. In fact, they're called literals according to whether they acquire a value of true or false, and they're related by a clause, an OR logic gate, and these clauses, which are constraints, are related by logical ends. Any Boolean, any combinatorial optimization problem can be written this way, okay, in what is called the conjunctive normal form. It doesn't matter, but it's generally writable this way. Now, the interesting thing about this is that you can transform this into a Boolean circuit with the OR gates representing the clauses and then the connections represented the ends, right? And these OR gates can have multiple variables if you have several variables in each of one of those. And then what you want to do is you want to know whether this is satisfiable, which means that all the clauses are satisfied, and so you have the full equation that I wrote there true, right? Now, if I have the answer, it's easy to check. I just plug it in and check whether that satisfies the answer. The problem is the reverse, right? I say I want all the clauses to be satisfied. The system has to find the literals or the variables assignments that actually do satisfy this problem. Now, this, as you can see, if it is a small, you can do it by hand, right? With 2, 3, maybe a few gates. But as soon as you start putting a lot of gates together, the problem becomes combinatorially difficult, right? It's extremely tough. But you see immediately here that what we would like is a type of gates that actually work in reverse. So they are able to acquire values from below, and they self-organize, or they try to organize it themselves to satisfy this problem. So, as I said, any combinatorial optimization problem can be written in Boolean format, as I just showed you. It's not even unique. In fact, some Boolean circuits may be better for certain applications than others. The important thing is that it can be written that way. And instead of using, so what we do, we use those circuits, but instead of using the standard gates, we will use the special gates. And that's where physics comes in. So we transform the standard gates into physical objects using time and locality. So here is an example of an AND gate. The truth table is here, and this is the symbol. And the important point of these gates, all of them, right, is that they are unidirectional. So once I give you inputs, I get an output, and that's it. I cannot do anything. But as I told you in that example before, I would like to go backward, right? Which means I want to give you an input, and I want to get the output that corresponds to the given input. Now, you cannot do that with the standard logic. But now suppose you actually transform this into a physical system where inside this gate, you have what we call memory variables. You have time and locality in the system. So the system can literally dynamically adapt to whatever signal comes from below or above. Now, in the future, I will just discuss electrical circuit realizations of this gate. So we represent, let's say, the input of these gates with the voltages of actual physical systems, and inside you have memory variables that actually allow the system to self-organize to the correct solution. You can do this in optics, you can do it in any other ways, but electrical circuits are the easiest one to build and also to scale in hardware. So suppose you have this new logic. What you want is to design literally physical systems such that if I here have let's say 1 1, it will give me 1, right? Which is this this logical proposition. But if I have here 1 1, I want the system to self-organize to give me only 1 1 on top. And if at the bottom I come here with a 0, I want this to give me the 3 possibilities, either 0 0, 1 0, or 0 1. Now, which one will be will win? Well, that depends now on the initial conditions, because all of a sudden I have a dynamical system. I have a set of and a dynamical system requires an initial conditions to set the solution, right? Okay, and once you build these things and you put them in a circuit, what happens is that they will try to self-organize, that will try to satisfy their own logical proposition by exchanging signals with the other ones. So they collectively try to solve the problem. So given an input, you will read the output at appropriate terminals. So we have transformed the original Boolean problem with the fixed gates that are unidirectional into a physics problem where we design complex systems like this one that collectively will try to solve the problem in reverse, right? So they will try to invert the problem that we're given. So that's the general idea. How do you do it in practice? Well, there are tons of ways you can do it. Here is an example again. Suppose this is an AND gate. And we have inside this objects that we call dynamic correction modules that operate like that, like this. I told you that these are electrical circuits. As I said, you can use anything else. suppose you have 1, 0, and 1, right? This is not consistent with the truth table. It's wrong, right? So this dynamic correction module reads the voltages of these two terminals, realizes that it's not in the correct configuration, and what it will do, it will inject current so that the 0 becomes a 1, and you satisfy this proposition. The bottom one reads the other two and says, I'm not satisfied. And so it takes current out and will try to move into 0 to satisfy this condition. So all of the three terminals will try to do that simultaneously. And again, which one wins? Well, it depends on the initial conditions. And of course, the type of problem you have and the configuration or the topology in which these gates find themselves. So all of a sudden, either you inject current or take current out of those terminals according to what's happening to the other corresponding terminals of the gate. And you can do this if you have 3 terminals, if you have 4 terminals, it doesn't matter. You can always try and design the gates in such a way that will try always to satisfy whatever logic truth table you have. In fact, in this paper below, we came up with a universal gate that can do XOR, OR, and no matter what, depending on the architecture, of course. And it can be realized using memory devices like resistive memories. Of course, you need also transistors as active elements to provide feedback, because you need to read these opposing terminal values of voltages and inject current or take current out, right? So these gates can be made using resistive memories or even transistors, because you can emulate the resistive memories using transistors. You don't need any special devices. You just use the CMOS, literally. Of course, not in the way we use it nowadays to make our computers, but you can build these things in hardware. And these gates operate either as regular gates or in reverse. In fact, they don't distinguish anymore between input and output, okay? So they are what we call self-organizing logic gates, because they self-organize into whatever logical proposition they have to satisfy, irrespective of whether the signal comes from the traditional input or the traditional output. Now, you can put them together. Let's say you want to solve a factorization or some other combinatorial optimization problem. And here is the incredible thing, because if you do this using electrical circuits or other type of devices, and you write down the equations of motion of these devices, right? The entire circuit that tries to solve a problem. Well, these are equations of motion for the voltages, the internal memory variables, currents, and so forth. Where you have these matrices that define the topology of the network that you're trying to solve. But these are ordinary differential equations. There are actually no linear dynamical systems, right? Where the variables are the currents, the voltages, internal states. And unlike a quantum computing, where a quantum state lives in a Hilbert space, which explodes exponentially with the number of qubits, a classical dynamical system its state lives in a phase space, which grows linearly with the number of degrees of freedom. All of a sudden, I actually can simulate these things in software, not just make them in hardware. I can literally take the equations of motion that come from, let's say, the hardware, and simulate them using even SPICE or whatever you want, right? So what I will show you are precisely these simulations. And before doing that, of course, you have a lot of mathematics that you have to work out. For example, dynamical systems, nonlinear dynamical systems can have periodic orbits. And if you represent the solutions of the problem you're looking at as equilibrium points, then you don't want to have periodic orbits. Worse, you can have also chaos, right? And if you have chaos, then all of a sudden you're not solving the problem. You cannot even simulate them efficiently. All right, so here is where a lot of mathematics had to come in, and I won't go into the details. We actually show that these are what we call point dissipative systems, which means they have a global attractor. And we can prove that the only equilibrium points of the combinatorial problems are the solutions of the problem to solve. The equilibrium points are reached exponentially fast. and the convergence rate scales polynomially with the system size. By the way, these are demonstrations done on the continuous dynamics, not on the discrete one. So if I simulate, I discretize time, and all of a sudden these theorems in principle don't hold, but as I will show you, they seem to be still satisfied. And if there are equilibrium points, which are the solutions of the problem, then you can show that there are no periodic orbits that coexist. And we prove this using function analysis. And in fact, you can prove that if there are equilibrium points, you don't have chaos. And you can prove it either using functional analysis or topology. I won't go into the details. You have tons of theorems that are in these papers if you're interested. So how do we solve the problem? Well, we selected, let's say, traveling salesman, then we transform it into binary representation. And this, as I said, it's a standard, and we know how to do that. And it's not even unique. In fact, for some problems, one representation may be better than another. And then we take that representation, that circuit, and literally replace what used to be an OR gate with our gates, a self-organizing logic gate, and what it was an AND gate with a self-organized AND gate, and so forth, right? And either you build these things, we haven't built these things yet, although we have plans to do that. But what I will show you are simulations, because again, these are not quantum systems. So you can simulate ordinary differential equations on our traditional computers using standard methods of integration. In fact, what I will show you are essentially using forward Euler, the crappiest method you can think of, using Matlab. And then you read the solutions, okay? So I'll show you simulations of these differential equations. We implemented them in Matlab. Of course, now the company has implemented this more advanced software, C++ or CUDA for GPUs and so forth. Incidentally, you can parallelize this quite easily and so forth. I won't show this thing. All the calculations have been done on a single processor using Matlab, using forward Euler as a simulation. So here's an example of factorization and of an 11-bit circuit. You have the circuit represented there with the dots being the input and output, but there's no distinction anymore between input and output. Black is 1, white is 0. And then we start from random initial conditions because we know the system will go to a solution no matter what. And if we switch on this, I don't know if you can see this clearly, but there are kind of waves that go around this thing. These are actually solitons. And in one lower dimension is what we call instantons. I will tell you in a moment. So they're topological objects. So let me rerun this. Maybe you haven't seen, but you have essentially waves that take care of eliminating logical defects. Remember that at the beginning, they're not satisfied at these logical gates, and these waves will try to get rid of those unsatisfied gates and leave the gates in the satisfied configuration, giving you the solution of the problem. It's like this. You have these waves that separate, regions of satisfaction and unsatisfaction, and they get out of the machine. Like solitons that move from one side of a, imagine a ferromagnet where you flip, spins on one side, the soliton moves and leaves the ferromagnet in the other ground state, right? Same thing. And if there is no solution, then it should stop here, but the system will keep on going because there is no equilibrium point, right? So it will never stop. For example, here is a factorization of a number which is already a prime, so it cannot find the solution because it doesn't exist. Now, as an example of this for a problem which is a little bit tougher, an MemComputing problem, which is Threesat, where you have three terminal gates, is represented like this. Here are the equations, if you're interested. By the way, this is published, it's not in preparation, it's already published. And again, we have voltages and memory variables. You can prove analytically, in fact, that again, in continuous time, this problem will be solved in a sublinear time, but that's not necessarily true in discrete time. So we did not prove NP equal to P if somebody, gets scared about seeing these results, because to prove NP equal to P, you have to prove that the same theorems hold also for the discrete time. Turing machines are machines that operate in discrete time. Our machines are non-Turing machines because they operate in continuous time. So the two are not necessarily equivalent. So for this, we remember that when you try to solve these problems, even if they're tough, you want to find tough instances. Otherwise, some problems, some instances could be easy, even for problems that are NP complete or NP hard. So there are, in fact, the instances that are very hard. They're easy to generate, but they're hard to solve, and they're used even in competitions, for example, SAT competitions. So we use those. If you're interested, you can take a look. And again, we use 4 Euler in Matlab using a single processor, no parallelization. So in the main panel, you see the results from our simulations for different ratios between number of variables versus number of clauses. And you can see that they all scale. This is a log-log scale. So the most difficult cases are when number of variables divided by number of clauses, sorry, number of clauses by number of variables is about 4.3. And in the but they're still polynomial. When you look at in the inset, you have a state-of-the-art algorithms, and notice the scale is log linear versus log log. In fact, this one at this point, each one of those instances would take about 15 hours for us to solve on a single core. It would take these more than the age of the universe to do it. In fact, they stop a pretty small number of variables, and so it's not easy for this to scale up, right? They scale exponentially, the standard algorithms. But this one represents a physical system actually is pretty fast, and as I said here, it's polynomial. Another example is when this is an NP hard problem where you are trying to find the optimum, right, in a non-convex landscape. In that case, what you're trying to do is maximize the number of satisfied clauses or minimize the number of unsatisfied clauses. So for this, we actually engaged the Supercomputer Center as an unimpeachable third party. So we gave them the code and they did the simulations, and they chose again tough instances, and they compared with the state-of-the-art solvers from SAT competitions, max SAT competitions in this case. It's a little bit old now as a competition, but here you have again time to find to go below a certain threshold of unsatisfied clauses versus number of variables. The standard, the state-of-the-art solvers explode exponentially, as you can see, and the other ones are instead the simulations of our solver scale linearly. In fact, again, if you try to extrapolate these two, it would take more than the age of the universe to reach, the result at 2 million variables, which took them 2 hours to solve on a single core. In fact, they actually pushed this to a huge number of variables, 64 million variables, about 1 billion literals. This is like integrating numerically about 1 billion couple ordinary differential equations running for about a day at this point, right? Using 4 Euler. So imagine the amount of numerical errors you have in this thing, and still scales linearly. And the limit was actually the memory. The memory also scales linearly. These are the ordinary differential equations, so you just need a linear scaling of the memory. At a certain point, they couldn't fit more than a certain amount of ordinary differential equations in the memory, which was 128 gigs of the processor they used. Now, I don't want to go into other examples, just because I want to show you the physics, why it's so powerful. But let me show you, other problems that we tackled so far. Tons of optimization problems done again by the Supercomputer Center, and ranging from random to max SAT, max SCAT, and so forth. And we compare with the winners of the max SAT competition. We're always better than those. We extended this to integer linear programming, and we solved 2 unsolved problems that were unsolved for many years. In fact, if you go on the webpage of the library, which is maintained in Germany, actually in Berlin, they say first the feasible solution found in computing for one of those problems. And we actually apply this to deep learning, and we have papers on this. So that is another interesting application where we can speed up and do unsupervised learning very efficiently, actually. I will show you the ground state of Ising spin glasses just to show you the physics behind this thing. And of course, the company works with other companies to solve very tough problems. By the way, many of those problems we don't even know what they are. They're given to us as black boxes in terms of just the conjunctive normal form of the problem, and we just provide the solution and the time to solution. So we don't even know what those problems are. They're tough because they typically explode exponentially, and the company succeeds most of the time in solving in linear time. If you're interested, you can take a look at this. So as I said, this is not a fluke. It's not an accident. We actually have tons of instances. So this has been tested. You can actually check yourself if you want to, use the software as a service to test some of the results I showed. Now, since this is a physics colloquium and people, want to know why in the world, you can do that, especially how is it possible that a non-quantum classical system can be so efficient, right? You hear about quantum supremacy of quantum computers versus classical systems, but remember that unfortunate name quantum supremacy refers to classical Turing machines. As I said, these are non-Turing machines. So there are dynamical systems that actually are designed to solve specific problems. Now, if you look at the voltages as a function of time of some problem, let's say factorization or some other problem, and you look at the voltages at the gates, you will see at the beginning the dynamics is very smooth, and then you see these spikes. Okay, these are not delta functions. If you zoom in, the width of those spikes is of order RC, where R is the resistance and C is the capacitance that we have in the actual physical devices we put in, right? So what the heck are these spikes? And in fact, these are the keys, are those solitons that you saw in the movie, and which we call instantons in one less dimension. So suppose you take one of those problems, factorization, right? And suppose you look at one of these spikes, and you look at the correlations between the voltages at different gates, right? You can always do it. So you fix the time, you look at the correlations about the voltages, you average over several, an ensemble of configurations. Well, the incredible thing is that you will see that these correlations, these correlations actually, I don't know what's happening. I lost the laser pointer. So these correlations are flat, which means that the machine, the voltages in the machine or the terminals of the machine are strongly correlated with each other, which means that a voltage at this point can literally correlate anywhere in the circuit. And of course, the correlations decay when you are at the edge of the circuit, right? It's like a superfluid. Essentially, the system gets into a superfluid phase where the system is rigid, right? Which means that the voltages being so strongly correlated, they will do the following, right? At the beginning, the gates, since the gates are connected locally, they will try to satisfy their logical propositions locally, right? Trying to exchange their terminals values locally. But then they realize immediately that they cannot do that, right? So if a gate says to the nearby gate, I want a 0, the other nearby gate says, well, if I give you a 0, I will be wrong, right? So they become immediately rigid. So the system becomes long range. It will be in such a way that a gate can literally correlate the change of variables with any other gate anywhere in the system. So you have a long range order, and you can actually show that this is also happening in time, not just in space. So to show you what happens physically, let's look at a spin glass, as a spin glass, which has a simple Hamiltonian. And in this case, again, you want to know the ground state. So you find build the spin glasses that are called frustrated loop instances, where you have loops of ferromagnets with just 1 ampere spin, so that it is very difficult it's easy to generate, but it's difficult to find the ground state because they are highly non-local objects. And so you know the ground state because it's a sum of single loops Hamiltonian. So here again, we did a test, standard state-of-the-art algorithms explode exponentially, simulated annealing, parallel tampering, even a commercial solver, Cplex. And this one, which we call Falcon, is was the name of the original solver, scales actually polynomially. But if you look in detail, if you look at the spins during dynamics, you see that without memory, the system gets stuck in this line of, it's a red line, right? So it will get stuck to a local minimum. With memory, any local minimum of the original voltages will be transformed into saddle points. So the system can get out of those original local minima. So you start from a discrete problem, right? Boolean problem. You transform first that into a continuous problem, and then you add memory. And the memory, what it does, it eliminates any local minima and transforms the local minima in saddle points. And so you have these jumps, which are instantons, in fact, or solitons. And if you look at what happens to the single spins, you create these clusters of spins that actually span the entire lattice. So all of a sudden, you have a long-range order in the system. In fact, if you look at the distribution of these clusters, it follows a critical Borel distribution. So this is the predicted analytical distribution. These are the numerics on the Threesat. So what happens is that the system self-tunes into a critical state. Once it enters into that critical state, it has long correlations so that voltages anywhere in the circuit can easily correlate and switch simultaneously. Now, that's why it's so difficult to solve those problems, right? Because if I want to, let's say, solve them using standard algorithms, I will say, well, let me switch, this variable and see what happens, right? But if I switch this variable, then all of a sudden other variables in other clauses will be unsatisfied, will render those clauses unsatisfied, right? And so you have to go back and forth and try to do this, and that takes time. But if you had a machine that actually knows or sees the whole problem simultaneously, well, you don't need that, right? Because simultaneously, this voltage can see what's happening very far away, right? And can flip as it needs to. So you can prove this. I won't go into the details. You can prove this using topological field theory, which is borrowed from high energy physics, in fact, because these dynamical equations are the easiest field theory you can think of, 0 plus 1 field theory. You can write in path integral formulation, which actually becomes a Witten type topological field theory. I won't go into the details. The important thing is that, as I told you, a physical system has to render an action stationary, and in our case, in our machines, the action is stationary in those paths in the phase space that connect the critical points. So points where the flow vector field is 0. So essentially what happens is that in phase space, you start from an initial point, which is not a critical point, but the system gets attracted to the closest critical point, and then which is a saddle point, and then it jumps, literally tunnels. Instantons are the Euclidean version of tunneling, right, into another critical point, which could be anywhere in the phase space, and then which, however, has to be more stable. Instantons cannot connect critical points that have the same level of stability. So it has to go from one that has a certain number of unstable directions to one that has more stable directions to one that has more stable directions until it finds the solution of the problem. So you can see even from this picture that the number of steps, the number of instantons to find the solution has to grow polynomially with problem size. Now, this is similar to the pinball machine I showed you at the beginning. So where the pop bumpers are the critical points, the zeros of the flow field, and the trajectories in between are the instantons, right? Now, it's the same thing. The ball or the state in the phase space have to render the action stationary, right? And so it will try to bounce, literally tunnel across the phase space, which is humongous, right? If you had to visit every point in the phase space, it would take forever, but it doesn't need to because it cuts across using these paths, which are called instantonic paths, right? like the ball will bounce around these pop bumpers until it finds the exit, which is, in our case, the solution of the problem. Now, the interesting thing is that since we can show that these are actually the matrix elements on these objects are topological invariants, even in the presence of noise, then you can shake this thing, you can put noise, numerical or physical, and it will still solve the solution unless you break the topology of the phase space. We did this numerically. In fact, you can put as much noise as you want, and these gates will still work. And this is the reason why I showed you at the beginning an example where we ran for almost a day, 1 billion couple ordering differential equations running with 4 Euler, as you know. And you know, if you teach computational physics, 4 Euler is the worst you can do because it should explode exponentially pretty fast, right? Well, it doesn't, and the reason is precisely because these machines use topological objects, which are essentially critical points and instantons between them. Otherwise, it wouldn't work. It literally would explode immediately. So what's happening? Well, the machine at the beginning, the gates, as I said, you know, try to solve this thing locally, but then they self-tune to a critical state, and from there they jump through these instantons anywhere in the phase space they need to, and that can happen. That happens in a polynomial way. So you need just a polynomial number of these objects to find the solution. So let me conclude so I leave a time for questions if you have some. So we introduced a new class of machines we call MemComputing machines. They're universal in the sense that they're Turing complete, but they're not necessarily Turing equivalent. So we haven't proved that they are Turing equivalent. They have features that Turing machines don't have. In fact, they operate in continuous time. Despite mapping, in this case, for digital machines, mapping integers into integers, they actually operate in time. Now, you can build this, as I told you, in hardware. You can use a CMOS, for example. You don't need any special materials. If you're working with the electrical circuits, you can do this also with optics. It doesn't matter. You can choose many other physical systems. But the incredible thing, unlike a quantum computer, so you can actually simulate the differential equations in software. This is a major advantage of quantum computers because, again, I can test this thing in software, and if it works in software, as I told you, you know, numerical noise is way worse than physical noise because numerical noise accumulates over time. So during dynamics, which means it's highly non-local. Typically, a physical noise is local, right, time and space. So it's much worse numerical noise than physical noise. So if it works in software, it has to work in hardware. And it is a type of topological computing, which is not quantum computing. So that's an interesting thing because we found another example of topological computing, but for non-quantum systems. And the topology comes precisely from the fact that these machines go through instantonic steps or solitons in higher dimensions. They employ topological objects to compute. And that's the reason why they're so robust. Otherwise, they wouldn't work. So we have applied this to machine learning optimization problems like the one I told you. We're working now on quantum Hamiltonians. You can apply it to many problems. Again, quantum Hamiltonians, if you represent wave functions using machine, in neural networks, for example, you have similar problems than the ones that I showed you. And you can do also real-time computing, but for that you need hardware. As I said, you can simulate, but remember that the simulations take time, right? So in hardware, you would be as fast as the slowest element you have in your hardware. In software, I'm limited by the numerical procedure, and so in software will be much slower in that respect. But for many problems, you can do calculations offline. You don't need real-time computing. So for many problems, you can do it. In fact, even the companies working with other companies for problems that don't require hardware. So here are the students that actually worked on this. Sean, who just graduated, Heike, Rudy, and Johan. I'm funded at the moment by DOE, DARPA, NSF, and by CMR, which is a center UCSD. and a little bit from the company. And thank you very much for your attention. I'll take any questions if there are any after this.
Okay, thank you very much, Max, for this very, very nice talk. Thank you very much. Are there questions, comments from the audience? Antonio, you have a question. Please go ahead.
Yes, first of all, thank you for this presentation. It's the first time I come across these systems, and I think I know a bit after your talk, so thank you. And once you have a problem, specific problem, how do you decide which architecture is going to solve it?
Yeah, that's a good question.
And then how do you know the solution is unique? I mean, this sounds like a challenging problem.
Okay, so those are two questions, right? So the first question is what architecture? So typically, this, as I told you, any combinatorial problem can be written in conjunctive normal form, which is a collection of OR gates separated by AND gates, right? So typically the problems that we write down, or the problems that the industry gives us, are written in that way. If they're in the integer linear programming format, which are algebraic problems, so you have inequalities, not just Boolean variables, we have this larger or equal than that, right? They have their own format. It's called MPS, but it's a different format. But essentially, we receive the format from either the companies, if they give us the format, or we generate ourselves the CNF file, the format. Now that is not unique. In fact, how you do it, and sometimes a format is more convenient numerically than another one, and that is a trial and error at this point. We don't have a clear understanding. It doesn't change the scalability, but it could change. It doesn't go from a polynomial to exponential, right? But it could change, prefactors, or even the polynomial degree to some extent. Remember that we transformed that into a landscape, a phase space landscape, into a physical system. So the two things, there is a step in there. Now, is there one or more solutions? Well, it depends on the problem, right? So if I have a factorization, there is only one solution because of the fundamental theorem of arithmetics. One solution in the sense, P times Q and Q times P, right? If you want to factor a number n in two primes. So one solution in that respect. If I have other problems, many of these problems, I have several solutions, right? Typically, you need just one solution, right? Which one will be chosen? Well, it depends on initial conditions, because if I start from some part of the phase space, I will go to one equilibrium point, which is one solution. If I start from another one, initial condition, I can go to another equilibrium point and another solution. Now, as I said, typically you don't need all solutions. But if you want them all, once you find one and you know there are others, what you do, you rewrite, or better, you generate a new Boolean circuit where the original solution is eliminated. So you actually, logically take it out. You see what I'm saying? In such a way that that is no longer an equilibrium point of the system. And you can repeat this, of course, in polynomial time, right? Every time you find a solution, you can eliminate it directly from the Boolean circuit itself. But again, as I said, typically you don't need more than one solution. So which one will be chosen depends on the initial condition. Typically, we don't know which one we're gonna get, because this is even for small between quotes problems. Even a single gate, you have phase spaces of tens of variables, so they're huge. So we don't know in which equilibrium point it will end up, right, according to the initial condition. Does it answer your question?
Yeah, it gives me a good idea. And just, taking the time, perhaps from others, but suppose you have an encryption done by a quantum computer. Could you tackle this and do this encryption?
It could be. We never looked at that, but you see, encryption is typically based on what people call one-way functions, which is essentially it's easy to check, difficult to find, right? Like factorization, or hash functions, right? That are used in cryptocurrencies. So these gates allow you to invert those one-way functions. So in principle, yes. Now, whether it's easier to do it in hardware than in software, I don't know. For example, factorization, we can now factor up to tens of bits, but the scalability is to the 5th power, right? And it's not very good from a software point of view. We're looking into possibility of speeding up the numerics, by parallelizing the code, using other types of tricks numerically. In hardware, if you build it as we proposed it originally, that scales quadratically or less. So you see what I'm saying? So it depends. It depends what you want to do. In software, sometimes the problem. I mean, it's always polynomial, but it's too numerically intensive to do it and scale it. As I said, for example, for the Threesat instances we looked at, the most difficult cases. For each instance, it took us 15 hours per instance. Those dots were 100 instances, the median over 100 instances. So imagine doing this over thousands of instances. Remember that, by the way, the problems that are given to us by industry, they run in the millions of variables, not in tens of variables. So numerics may be good for certain types of problems. Otherwise, you have to go into the hardware. But in principle, if the problem is, as I said, a one-way function, these new gates allow you to invert those functions, whatever they are, whether in software or in hardware. Does that answer your question?
Great. Thank you.
You're welcome.
Okay. Are there further questions, comments? Yeah, Max, I have a related question. So if I understood correctly, you have an algebraic problem which you represent by a Boolean network, right?
Mm-hmm.
And yeah, you solve this network and you convert it into a dynamical system, which you have solved with software in the computer. Mm-hmm. And when you implement it as a hardware circuit, do I understand correctly that you need a new circuit for every new problem, right?
Yeah, correct. You can, so there are two ways, right? So you can either do it like that. So for every problem, you have a different hardware, or you use FPGAs that allow you to create architectures that are can be programmed externally. So you can switch from I don't know, doors to ends and so forth. So FPGAs is the easier path I can see for a general purpose type of architecture. But if you want something that is specialized, for example, if you want to do pattern recognition, want to accelerate training of neural networks, you just have one type of architecture. But if you want to solve a combinatorial optimization from various optimization problems, you can use FPGAs to switch from one architecture to the other.
Okay, I see. Yeah, and my related question to this is from when you implement it on hardware, from where is the computation time coming from?
Yeah, so, yeah, of course the
because I was getting it was solved immediately.
That's right. It's immediately within the time scale of what is the slowest element. So it is limited by the RC time in the circuit.
Yeah.
And essentially the slowest element in the system. So if you have the slowest elements of being in the milliseconds or microseconds or nanoseconds, those determine the speed. Yeah, they don't. Hardware doesn't discretize time, right? It will do it in one shot. Yeah. So that's why I was saying, if you want to, for example, use it for pattern recognition in autonomous vehicles, where you need to collect external information and process it essentially instantaneously, you cannot do it in software. You have to do it in hardware, and you have to have a specialized hardware that does the training of the neural network on the fly. So that is, in fact, we already showed theoretically that you can do it. You can actually use this idea to do that, do unsupervised training efficiently using MemComputing. But if you want to deploy it on cars, let's say, and then you have to do the hardware. And at that point, it would be as fast as whatever is the switching time of the slowest element in the circuit. typically you can switch in nanoseconds, right?
Yeah.
Or hundreds of nanoseconds transistors. So I would imagine that is the time scale of this.
Okay. Yeah, that sounds great. Thank you very much.
Thank you for inviting me. It's a pity that I cannot be with you at this time. But
yeah. Are there further questions from the audience?
Yeah, sure.
Let me see. Yeah, this doesn't seem the case. So thank you again, Max, for this very nice talk. Yeah, and it's a pity that you cannot be here. I hope so the next time.
Next time
here in Cuernavaca.
All right.
Okay.
Bye, guys.
Thank you. Bye.
Thank you, guys. Bye-bye.